Now let's see how we can construct the tangents from an external point exactly through the geometrical understanding or through the geometrical instruments to an accuracy to its best. So how do we construct the tangents from an external point? So let's see the construction in a stepwise process. So initially, let me assume a circle with a suitable radius and center O. So therefore, if I have a circle with center O, then I know that I can draw two tangents if I take an external point P outside the circle. The third case, as we have already discussed. So for a point P, there are two tangents which can be drawn from the external point P. Therefore, we don't know where exactly the two tangents can be drawn. I just construct using the geometrical properties. So to identify the points A and B on the circle is what is entirely about the whole construction. So how do we locate the points A and B on the circumference is the biggest question here in a successful construction of tangents from an external point. Therefore, let's take an external point P from where the two tangents have to be constructed. So here I join the points O and P using a ruler. So joining the points O and P, I get a line segment OP which is from P to O. Now I find the midpoint of PO using the bisector concept. I take the compass which is more than half and I just cut the arcs out here and this out here, and once I cut the two arcs, I join them so that the intersection will give me the midpoint of the line segment OP. So using the compass concept, taking more than half and cutting the bisectors and then joining the line of the point of intersection of the two bisectors, I get the perpendicular bisector of OP, which in turn gives me the midpoint of OP. Now once I get the midpoint, I just take the measurement of OM as the radius and draw a circle. So using the compass, I just draw a circle with as this. I draw a circle with this as the radius. Now with OM as radius, once I draw the circle, I clearly identify that this bigger circle cuts the smaller circle at 2 points A and B. The points of intersections of A and B are nothing but the located points where if I draw a line through PA will be one of the tangent for this circle with center O, and if I draw a line PB, then this will be the other tangent for the circle with center O. That is, when I take this point P and join P with A, and then I join P with B, I get the two tangents from PA and PB. Of course, PA equal to PB from the previous theorem is how I can draw the two tangents from an external point. So let's recap with once again on how we have constructed the two tangents using the geometrical properties. Initially, I take a circle with center O and I take the external point where from the external point to the center, I draw a line, which is the line segment PO. Now, once the line segment PO is considered, I locate the midpoint of PO by using the perpendicular bisector concept. We all know that we take the compass more than half and cut up and down, and that line passing through point of intersection cuts exactly in the middle of and perpendicular to OP. Now, once I locate the midpoint M, I try to take OM as radius, and using a compass, I draw an entire circle passing through O and P. Obviously, it passes through P because these two distances are equal. They act as the radius for radii for the bigger circle. So drawing the circle, I get the bigger circle which cuts the smaller circle at A and B. Now the circle which cuts at A and B are located as A and B, and then joining P and PA and PB are nothing but the required tangents for the circle with center O. So once I get the tangents PA and PB, they are nothing but exactly the two tangents which can be constructed from an external point. But the biggest question here is why? Mathematically, I want an evidence on why this bigger circle cutting at A and B exactly makes us evident that these two are the tangents is the biggest question. Maths is not about assuming, maths is about proving the results. So how do we prove that what we have taken are mathematically valid for being the tangents? Why is it that this circle cutting here makes the tangents is the biggest question for here. So let's see. Clearly, when I take the bigger circle, my radius, my diameter here is PO for the bigger circle. Now since PO is the diameter, if I just join A with O, I get this to be 90 because this acts as the semicircle for the bigger circle. Therefore, with M as center and OM as radius, I got the bigger circle where I join AO, I get triangle PAO is a right angle triangle right angled at A because angle in a semicircle is 90 degrees. Therefore, this angle will be 90. Now, indirectly, I have the radius perpendicular to tangent because angle in a semicircle is 90 degrees for this bigger circle, but if you take the smaller circle, I get the same angle to be the radius which is perpendicular to tangent. Because this angle is 90, this must be a radius and this must be a tangent to that radius. Is how we conclude using the concept of radius perpendicular to tangent. So mathematically, since the angle in a semicircle is 90 degrees, therefore that 90 degrees helps us in locating this to be the line which is perpendicular to the radius, and hence by the theorem radius perpendicular to tangent, this must be a tangent to the radius or to the circle with the radius passing through the point of contact, and hence the two tangents are PA and PB is how we conclude. Now let's see some properties of tangents. Already we have discussed about many properties in tangents. Radius is perpendicular to tangent and the length of the tangents are equal from an external point to the circle is how we have seen some of the properties of the tangents connected with the circle. Similarly, let's see some extended properties of the tangents which are also very useful. Initially, to start with, the concentric circles. So let's take two circles which are concentric to each other, that is concentric in the sense with same center. If two circles are concentric, implies the two circles are with the same center. Now in this case, let me draw a chord for the bigger circle. Say this is the chord or the secant for the bigger circle AB. So the chord or the secant of the bigger circle AB makes us understand that this is a tangent to the smaller circle. I take the chord for the bigger circle in such a way that it touches the smaller circle in this manner. Now since AB is the secant which touches the circle, the smaller circle, therefore I understand that AB is the chord or secant for the bigger circle, but AB is the tangent to the smaller circle because it touches at, say, point P. Is how I understand. AB is the chord for the bigger circle and AB is the tangent for the smaller circle, tangent at P. Now let me join OP. Now I need to prove here that P bisects AB. That is, the point of contact in this situation always bisects the chord AB is what we need to prove here. That is, when I have the point of contact for the smaller circle must bisect PB. That is, I have to prove that PA is equal to PB is what I need to prove in case of the concentric circles, the bigger circle and the smaller circle. So for this, let's join AO and BO so that I get this perpendicular to this and this perpendicular to this, because radius is perpendicular to tangent for the smaller circle. So here the construction is, so here I join OA and OB. Also I join OP. Now in this case, my required to prove is PA equal to PB. Therefore, let's see how we can prove this using the two triangles AOP and BOP. So to start with the proof of the statement. Now for these two triangles, let me take, considering triangle OAP and triangle OBP, clearly I see that these two triangles are congruent, as I can see that one of them is 90 and one of them is the common side and the third side is the radius. By SAS or RHS congruency, I have these two triangles congruent. That is, if I start with OA is equal to OB because of same radii. Is the same radius, therefore this must be equal to this. Next, my OP is equal to OP because it is the common side for the two triangles. Therefore, this is because of the common side property. Similarly, angle APO is equal to angle BPO, which is equal to 90 degrees. That is, angle APO is equal to angle BPO, which is 90 degrees. Since radius is perpendicular to tangent is what we have already discussed as the theorem. Now clearly I see that this is right angle, this is hypotenuse, and this is one of the side, which again makes me remind of the RHS congruency through which the two triangles OAP and OBP are congruent. Therefore, for this triangle, by RHS congruency, I can show that, I can prove that triangle OAP is congruent to triangle OBP, are the two triangles which are congruent to each other. Now therefore, because the two triangles are congruent, they are equal in all respects with angles and sides. Therefore, the sides must be equal. Therefore, this triangle with the side AP must be equal to the other triangle with the side PB. That implies PA must be equal to PB, is what we have proved through the congruency of two triangles. Therefore, PA is equal to PB implies P bisects AB, is what the statement concludes, is how we get. Therefore, when I draw a chord to the circle, then the other concentric circle where the chord acts as the tangent will exactly be the midpoint. That is, this bisects, P bisects AB such that PA is equal to PB, is what we have proved in case of this theorem. So let's take the next property, the extended properties of tangents, where the property says that if I have a circle with an external point P, then I can draw two tangents. So let's draw the two tangents to the circle, one of them here and one of them here, this and this. Now here I need to prove that, let me take this external point as E and my center as A and this as P and Q, so that my points are P and Q. Now, if I join P and Q and then join with this and this, then I had to prove that this angle is twice of this angle, is what we need to prove. So let's see how we need to prove this. So if I consider a circle with center O and A is any point outside, I can draw two tangents from the external point A, that is AP and AQ are the two tangents. So using the two tangents, let's see how I had to prove angle PAQ is twice of angle OPQ, or it is also twice of angle OQP, is what I need to prove using the diagram. So this is the required to prove part. So how do I do the proof? So clearly I see that from A I have AP equals AQ. Therefore, triangle APQ is isosceles triangle because two of its sides, AP and AQ, are equal. APQ is clearly an isosceles triangle since AP is equal to AQ. Now, let me take this as theta. Now, clearly, I identify that if this is an isosceles triangle, this angle and this angle must be same by isosceles property. That implies angle APQ is equal to angle AQP since by isosceles property is what I get from isosceles property. So if I take this as x and theta, then clearly I identify that if this angle is theta, this is x and this is x, then x plus theta is 180 degrees. Because sum of three angles in a triangle is 180, this will be equal to 180, so that 2x is 180 minus theta, or I get x equals 90 minus half theta is what I get from sum of three angles of a triangle. So in this case, x equals 90 minus theta by 2. But we know that x is angle APQ or AQP, which is 90 minus theta by 2. Now next I consider the angle OPA. Therefore, angle OPA, as I see in the diagram, is OPQ plus QPA is what we get. Angle OPQ plus angle QPA is what I get when I split the entire angle into this angle plus this angle. So this plus this is the entire angle. So let's see what I get when I simplify further with this. That implies my angle OPQ, which I'm going to find, would be angle OPQ on the left hand side is equal to angle OPA QP. OPQ is angle OPA, which is totally which I need to find. Now let's see what angle OPQ is from here. That implies angle OPQ as angle OPA minus angle QPA is what I get when I take this to the left hand side. Now as I clearly see here, angle OPA is 90 degrees because OP is the radius and AP is the tangent. So radius is perpendicular to tangent, therefore this entirely is 90 degrees. Therefore OPA is 90 degrees and my angle QPA is x, is what I get from the diagram. But as I clearly see here, I get that my angle OPQ is nothing but 90 minus x. X is already substituted to be 90 minus x by 2, which we have already proved for x, which is 90 minus theta by 2 is what we got. So simplifying this further, I get this to be 90 minus 90 plus theta by 2. Therefore, this on cancellation gives me theta by 2, which clearly makes me understand that theta, which is angle PAQ, therefore substituting for theta, angle OPQ is angle APQ PAQ by 2. When I further simplify this by cross multiplication, angle PAQ is twice angle OPQ is what I get from the given proof. Therefore, angle PAQ is always twice of angle OPQ is how they are connected. Similarly, proceeding with the same proof, taking this angle, that is angle OQA is OQP plus PQA, and then going along the vertex Q in the similar manner, I prove that similarly I get angle PAQ or QAP is twice angle OQP, which I can prove through the similar proof. Hence, these are the two properties which are identified for the external tangents drawn from an external point A, where the angle between the tangents theta is always twice of the angle between the radius and the chord of the either angles, which I get as OPQ and OQP, which are always half of the given angle PAQ. Now let's see the last property in connecting the tangents to the circle, the extended property out here. So let's take a circle in which I want to draw for each of the point of contact. When I draw the tangents, I get a quadrilateral ABCD where the points of contacts are PQ, RS. That is, a quadrilateral which is obtained by connecting each of the tangents drawn at PQ, RS on the circle is what I get with the circle, of course, inside the quadrilateral, because the tangents are always outside the circle, touching the circle. Therefore, the quadrilateral obviously should lie and circle inside and a quadrilateral outside. So with this quadrilateral, I would like to prove that my required to prove part out here in case of this quadrilateral is that I had to prove AB plus DC is equal to BC plus AD. That is, when I add the opposite sides in pair, they must be equal in case of this quadrilateral. So my proof is that I have to prove AB plus DC equals BC plus AD is what I need to prove in case of this. So as I clearly see here that the proof is totally reliable on an external point from where two tangents are drawn. That is, when I take each of the vertex of the quadrilateral ABCD to start with the vertex A. Now, the first vertex of the quadrilateral ABCD is clearly passing through two tangents. That is, for an external point for the circle, there are two tangents AP and AS which are equal, because we have already seen the property that from an external point the lengths of tangents are equal. Therefore, AP must be equal to AS. Similarly, BQ must be equal to BP. This must be equal to this, and this must be equal to this. Is how we get each pair equal to the other, because the lengths of tangents from an external point are equal. So using that condition, let's prove AB plus DC equal to this. So let's see how we can do the proof of this theorem. So considering the proof, let me consider AB plus DC on the left hand side and prove the right hand side from the LHS. So LHS being AB plus DC is what I consider, and clearly when I take AB, I can split AB as AP plus PB. Therefore, I can split AB as AP plus BP. When I add together, I get AB, as can be seen from the side AB. Similarly, I can split the side DC because DC can be written as dr plus cr, which on the whole makes the whole of DC. Therefore, splitting DC as dr plus cr is what I get when I split each of the sides AB and DC through the respective points PQ, RS, or P and R. Now here, AP is clearly equal to AS because the lengths of tangent from an external point A are equal. Therefore, AP is equal to AS. In place of AP, I write AS, as can be clearly seen through the lengths of tangents, this being equal to this. So AP equal to AS, I replace AP with AS. Similarly, my BP is equal to BQ with the similar property. So therefore, in place of BQ out here, I write BP. Instead of BP, I write here BQ is what I write here. Similarly, when I have dr is nothing but equal to ds, therefore in place of dr, I write ds. And lastly, cr, which is equal to cq, I write here cq for each of the properties. Now next, what I do is I compare this and this and this and this. Therefore, pairing them, as plus ds plus bq plus cq is what I get when I pair them alternatively. As can be seen in the diagram, as plus ds is clearly ad on the whole, because as and ds add up to give the side ad of the original quadrilateral. Therefore, this is in turn giving me AD, and plus this in turn gives me BQ plus CQ, can clearly be seen as BC. But this, when rearranged, gives me BC plus AD, which is clearly the right hand side of the required to prove. Therefore, I clearly prove that AB plus DC is equal to BC plus AD, hence proved. It's how we understand through the lengths of tangents from the external point, which make the quadrilateral ABCD from the circle PQRS. Segments of a circle. What are segments? As we have discussed about the tangents and the radius or the chord or the secant, similarly, a segment is also one of the important concepts or the property of a circle. So let's see what a segment is for a circle. So let's take a circle with center O, and let me say I have a chord AB or a secant AB to the circle. Now, what is the significance of the chord in the circle is the biggest question here. A chord divides the circle into two parts, is the other way of understanding a chord or a secant. So as we see the chord AB, this clearly divides the circle into two parts, where one of the part is this and the other part is this. Is how I get two different regions. Now, how do you understand the difference between this region and this region is very important in understanding segments of a circle. So in this case, a segment is an area which is obtained when the chord divides the circle into two parts. Therefore, I get two parts where one of the region is given by this, which is called the minor segment, and this, which is called the major segment. The reason being that this is minor in shape and this is major in shape. Now, let's see what this shaded region is called. Now, this part of the shaded region is called major segment because it is major in its area. But mathematically, how do you say that this is major in area or minor in area without actually measuring the area? Mathematically, this is called a minor segment because this does not include center of circle. but major segment always includes center of circle is a very important note out here. So this is called the major segment. This shaded region is called the major segment because this includes center of circle. This does not include center of circle, but this includes center of circle. Therefore, this whole area is called the major segment, and this whole region is called the minor segment. So the learning outcome here is that a chord or a secant plays a vital role in defining the segment of a circle. But let's take a special case. What is the special case out here? If I have a circle with center O, and if my chord AB is the diameter, then what happens? How do you define the segments for a chord which is reaching up to the center of the circle, or if the chord is the diameter, is the biggest question as a special case. So in case of special case, we identify that we have exactly two equal areas. One is the major, or one is the minor segment, converge to become two equal segments where both are called semicircular areas. So in this case, I have each of this and each of this are called semicircular areas. And also, interestingly, if the chord tends to become a diameter, major segment will be equal to minor segment, as we have seen here. Then in this case of the special case, major segment is equal to minor segment, is what we conclude for the special case. So how do I find the areas of the different segments using the formulae is the biggest question out here. How do you find the formulae? So let's see how we can find the area of the minor segment or area of the major segment connected with the areas of the sectors. Now let's see how we can find the area of the minor segment and area of the major segment respectively. Therefore, let's use some of the geometrical properties to find area of the minor and the major segment. Before we find the area of each of the segments respectively, let me construct by joining OA and OB. Now since OA is equal to OB because they are of the equal radii, let me take the radius of the circle as R. Radius of the circle as R, and let me take the angle subtended at the center is x degrees, is what I get. Therefore, as I clearly see, the minor segment is the shaded region here. Therefore, in this case of the area of minor segment is given by area of the whole sector minus area of the triangle is what I get. So area of minor segment is area of sector OAB minus area of triangle OAB is what I get, the area of minor segment. Now as the sector minus triangle gives me this minor segment, now we have the respective formulae for the sector, which is given by its area as x by 360 times pi r square minus area of triangle OAB, which can be done with various properties like half into base into height or any other respective formula if the height is given, minus area of triangle OAB is what I get as the derived formula for area of minor segment. Next comes the major segment. Now how do I find the area of major segment? Major segment can be found, the area of the major segment can be found if we know the area of the minor segment. Therefore, area of major segment is given by the formula area of the whole circle, the entire circle, minus the minor segment gives me the area of the major segment, because this removed from the entire circle gives me the major segment. So area of circle minus area of minor segment is what gives me area of major segment. But area of circle we already know is pi r square minus area of minor segment, which I already calculated to be x by 360 into pi r square minus area of triangle OAB is what I get as the formula for area of major segment. Therefore, with these two basic formulae for area of minor segment and area of major segment connecting the circle and the triangle, we find for any situational problem where we need to find the segment which is minor and the segment which is major, finding the areas through the sector concept. This is how the formula is derived. Now let's find the area of the minor segment, which clearly makes me understand that area of waterbed, which is area of minor segment, is nothing but the minor segment, which is area of sector minus area of triangle OAB. Therefore, area of sector minus area of triangle OAB is what I get as the whole area of minor segment. Now, how do we find area of sector? We all know that the formula for area of sector is x by 360, x being 90, into pi r square, that is pi r square, that is 49 times square, minus area of triangle OAB, which I need to find from here, makes me clearly understand that this will be a perpendicular drawn here, makes 90 degrees. Therefore, area of triangle OAB will be half into base into height, but I don't have the dimensions here, so I utilize the condition of finding the area of triangle using this measurement. So let's see how we can find area of triangle OAB using the given dimensions. Now clearly, I see that this being 90 degrees makes this as the base and the height of the triangle. Therefore, for this right angle triangle, the area of the triangle is directly given to be half times base into height. The base being 49 and the height being 49, OB and OA respectively. Therefore, this being a right angle triangle, I get half times 49 times 49 as the base and height. So simplifying this, I get this to be 9 ones, 9 fours. So 1 by 4 times pi, if I take it as 22 by 7, this reduces to 49 times 49, and further simplification gives half times 49 times 49. Now this on further simplification gives 2 times 2, 2 11s, 7 ones, 7 sevens. Therefore, this on further simplification, I can take 49 over 2 common and then simplify with even 7 taken outside. So the rest of the terms I put there inside. So 7 times 49 by 2 is out. I have 11 inside, and then this 49 by 2 and 7 out will keep 7 remaining, which is inside. Therefore, simplifying this further, I get this to be 49 times 7 over 2 times 11 minus 7, which is 4. Therefore, this on cancellation gives 49 times 2, which is 98 times 7. 7 8s 56, 7 9 63 plus 5, which is 686 of meters square. So this is the area of the waterbed covered by the entire circular park, is how we understand. Now it is very important to note that I have taken pi as 22 by 7, but note that until and unless the problem says use pi as 3.14 or etc., you have to use pi as 22 over 7. Now using this, I have area of waterbed is 686 meters square. Therefore, my area of the circular park, which is not covered by waterbed, is area of major segment, that is indirectly to be found, is area of circle minus area of the waterbed. Area of circle is pi r square, which is clearly pi times r square minus area of this, which is 686. This on simplification gives 22 by 7 times 49 into 49 minus 686, which on gives 7 sevens. Therefore, this on simplification gives me 686, which is written indirectly as 49 times 7 times 2. Therefore, 7 times 49, which is taken common on both these cases, gives me 22 minus 2. Now, to continue with, I got this as 7 times 49 times 22 minus 2, which on further simplification gives me 7 times 49 times 20 is what I get. To simplify this further, 7 times this is 980, and this on further simplification gives 7 8s 56, 7 9 63, 6 8 60 is meter square is the area of the complete region which is not covered with waterbed in the entire park. So area of the circular park which is not covered with waterbed, that is the area of the major segment, is nothing but 6,860 meters square, is how we understand the areas of the segments connected with the areas in real life applications.